Hello everyone, my name is Bruna Araujo. I'm a master's student of Federal University of Santa Catarina, and I'm going to present the paper called Implementation Evaluation of Adaptive Cache Insertion Policies for Real-Time Systems. This paper was written by me, Giovani Gracioli, Tomasz Kloda, Denis Hoornaert, and Marco Caccamo. So the cache memory is one of the most popular mechanisms used to improve the average performance of the modern cyber-physical systems. Every time that required information is not in the cache, it must be placed from main memory in some line of the cache. So the replacement policy is responsible to choose the evicted cache line. However, the high time penalties that a cache miss can cause make of the cache a big source of unpredictability, directly impacting real-time systems once those systems need to meet strict time constraints. In the context of hard real-time systems, designing and implementing a near-optimal cache eviction policy is essential, as the gains in execution time have a direct impact on the scalability ratios and the utilization of the target platform. Standard and state-of-the-art cache architectures feature either the random policy, the first in first out policy or FIFO, the last recently used policy or LRU, or the pseudo LRU policy. The first two are simple to implement but has a bad average performance compared to LRU. On the other hand, LRU-based policies are susceptible to trash when the required application data is greater than the available cache. Because of this, Gracioli et al. Proposed simple change to the insertion policy to reduce the number of cache misses for memory-intensive applications. Named these new policies as adaptive insertion policies. They are LRU insertion policy, as known as LIP, bimodal insertion policy, or BIP, and dynamic insertion policy, or DIP. Besides those policies had presented interesting results when compared to LRU, their impact on the scalability of real-time systems has not been studied yet. Moreover, the original DIP evaluation has not studied its behavior when varying the number of ways and the impact of the cache miss counter size. So, the contributions of this paper are the implementation of the adaptive cache policies into an open source cache simulator called CacheGreen. This way, we were able to extend the analysis of the DIP adaptive insertion policy considering the context of real-time systems, and evaluate the behavior of the policies when varying the cache parameters. Moreover, by applying the reduction on the number of cache misses of the DIP policy into the scalability analysis, we were able to observe its impact on the scalability ratio of real-time systems. The cache simulator used was the CacheGreen, an open source tool provided by Valgrind that requires as input the cache partition size, the number of ways, the line size, and the replacement policy, and generates a detailed profile of the whole cache hierarchy as the number of access and misses to the first and last level of the cache. Whenever there is an instruction or data reference, CacheGreen simulates the cache access using either an instruction or data cache. The target cache is passed as parameter in the call to the isMiss function, together with the address set and tag. Within isMiss, the appropriate cache eviction policy is applied for a function pointer to the function which implements the eviction policy algorithm. We modify this part of the CacheGreen by adding functions for each adaptive insertion policy. If there is a miss in the first level of the cache, then CacheGreen calls again isMiss, passing the last level of cache as parameter. This listing shows the implementation of LIP into CacheGreen. SetNo represents the number of set, and CSOS represents the cache associativity. In line 3, the required tag is retrieved. If this tag is found in the cache, then it is promoted to the most recently used position and shuffle the rest down, as shown in line 6 and 7. In line 9 is show what happens if a miss occurs. So the incoming line is inserted into the LRU position, or the last recently used position. Now this listing shows the implementation of BAP. It's important to notice that BAP behaves as LIU or LIP for any cache hit by promoting recently accessed line to the MRU position, or the most recently used position, as is shown in line 3, 4, and 5. But when a miss occurs, BAP will need the bimodal throttle parameter to define how the policy will behave. Together with the bimodal throttle parameter, a randomly generated number, prob, are used to define the behavior of BAP. As shown in line 8, if this random number is greater or equal than the bimodal throttle parameter times 100, BAP will behave as LIP. Otherwise, it will act like LRU. The DAP implementation followed the global mechanism, which uses two auxiliary tag directories with copies of blocks from the main cache. In each directory, the LRU and BAP policies are applied exclusively. The policy used in the main cache is the one that counts the least number of cache misses in the respective directories. For this, a binary counter named pcell is incremented at every miss that occurs in the directory under the BAP policy, and is decremented whenever a miss occurs in the directory under the LRU policy. So, if the most significant bit of pcell is 0, LRU policy is used. Otherwise, BAP policy is used in the main cache directory. It's important to see that pcell is a binary counter and is always initialized in the middle of its range. So, for example, for a pcell with 4 bits, its range goes to 0 to 15 in bits. So pcell is initialized in the 1000 that equals to 8. So if pcell is greater or equal to 1000, it will be applied the LRU policy. If pcell is smaller, then the BAP policy will be used. For evaluation of the BAP and DAP implementation, two benchmark suites were used. Mi-Bench suite represents soft real-time applications, and Cortex suite represents hard real-time applications. The benchmarks have been executed for a wide range of configuration, as the total cache size, the number of ways. The cache replacement policies used were LRU, BAP, and DAP. Additionally, in the case of DAP, the size of pcell is also subject to variations. However, the cache line size is fixed to 64 bytes for all the experiments. The BAP throttle parameter was set to 1/64. The first experiment evaluated BAP and DAP and compared them to a LRU with respect to the amount of cache misses each benchmark experienced for the policy. The figure displays the results for PCA small and SVD3 small. Each of these benchmarks is simulated in a platform assuming an 8-way associative cache with the total size represented in the horizontal axis, and for different eviction policies shown by the bar cluster, with LRU being the blue bar, BAP the orange bar, and DAP the green bar. The pcell counter has a size of 10 bits. The amount of cache misses for each cache configuration is reported on the vertical axis and is normalized according to LRU. So, within each bar cluster, a smaller bar than LRU implies that the policy has fewer cache misses and thus a reduced execution time. A first observation from the results concerns the behavior of the DAP policy, that always tends to replicate the performance of the best policy between LRU and BAP for a given cache size, as is expected with the global mechanism. Another observation shows that BAP and DAP are not always better than LRU. In each of them, we observe a range of cache size for each the amount of cache misses is smaller than LRU. These ranges vary from one benchmark to another. For instance, PCA small experience fewer misses using BIP and DIP for cache sizes ranging from 16 kilobytes to 512 kilobytes, while SVD3 presents best results in the range from 2 kilobytes to 8 kilobytes. These variations means that the efficiency of the adaptive insertion policy depends on the amount of data needed by the benchmark and the cache size. In the original paper introducing the DAP policy, the size of the pixel counter is arbitrarily set to 10 bits. However, its size can potentially influence the policy switching decision. So the objective of this set of experiments was to evaluate the impact of the pixel size on the amount of cache misses occurred during the execution of PCA small benchmark. For this experiment, we assume a 128 kilobyte large 8-way associative cache and run the benchmark using the LRU, BIP, and DAP policy. We vary the size of pixel on the horizontal axis and report the amount of cache misses occurring on the vertical axis. Each bar is normalized over the cache miss occurring using LRU. PCA small is slightly affected by the pixel counter size, as we can see in the figure. For a small pixel size, DAP incurs more cache misses than BIP policy. However, as the pixel counter size increases, the gap between DAP and BIP fades away. We can conclude that the pixel counter size influences the execution of tasks and that a large size enables DAP to approximate the optimal choice of policy. The next experiment aimed to understand the relationship between the associativity of the cache, the eviction policy, and the amount of cache misses that a given benchmark will experience. The results are displayed in the figure. The selected benchmarks, PCI small and SVD3 small, both highlight a different behavior. In the case of PCA, we can observe that the amount of cache misses decreases linearly as the associative increases, reaching a plateau at 16 ways. The good performance of BIP can be linked to an extremely sequential workload with low data reutilization. On the other hand, for SVD3, the BIP policy fails to outperform LRU, hitting and workload with higher data reutilization. Globally, note that DAP is useful in always closely following the best performing policy. The objective of this experiment was to understand the evolution of the pixel counter during the execution of selected benchmarks. To this end, we instrumented our extended version of CacheGreen to collect and log the pixel counter content. In this set of experiment, we assume a 128 kilobyte large 8-way associative cache have a DIP for eviction policy and feature a 10 bits wide pixel register. The pixel counter is initialized with the value of 512, meaning that LRU is initially the policy selected. This frontier value separating BIP and LRU policy is drawn in red. Regarding the PCA benchmark, one can clearly see that evolution of the pixel value through the execution is segmented in two distinct areas. According to the pixel value before the 10,000 instruction, the LRU policy is applied. Thereafter, the BIP policy is applied, meaning that this policy is the most adapted to this section of the program. For the schedulability impact evaluation were generated 10,000 task sets. Each of them contains 8 tasks. We vary the utilization from 0 to 1 with a step of 0.01 to generated uniformly distributed random task utilization values that sum to the total utilization. For each task utilization, we randomly generated a parity value ranged from 10,000 to 1 million microseconds with log uniform distribution and obtain the task WCT. Tasks have implicit deadlines and are assigned priorities based on the rate monotonic policy. The task set for BIP and DIP are obtained from the LRU task set by scaling the task's worst case execution times by the scaling factors from PCA small and SVD3 small benchmarks. Figure A shows the scalability ratio where the scaling factors of all tasks are based on PCA small, and Figure B, the scaling factors are based on the SVD3 small benchmark. PCA favors BIP and the later LRU. The results for PCA show significant improvement of BIP over LRU, reaching over 50% for high utilization rates. For SVD3s, LRU only slightly outperforms BIP. Most importantly, in both cases, BIP always follows the best policy, incurring very little overhead. So in this work, we perform an evaluation of the LRU-based adaptive insertion policy, LIP, BIP, and DIP. For this end, we observe the impact of the cache geometry for each policy compared to LRU, and we investigate the impact of the counter-selector PCL in DIP. The obtained results from a simulation environment have shown that the cache size and the associativity play an important role in the performance of the adaptive insertion policy, while the variation of PCL size are not that important. As future work, we plan to implement and evaluate DIP in an open processor architecture such as RISC-V and explore the choice of cache-related parameters to improve the replacement policies, aiming at real-time applications. And that's it. Thank you all for the attention.